All right, we're ready to start? Okay, I'll make a start because we've got to push on through this. So we've only got half an hour to talk through this. So my name's Gareth Thomas. I'm a developer technology engineer for AMD. And the plan today, we're going to talk about compute-based GPU particle systems. So there we are. So the plan is I'm going to quickly give like a quick overview of how to build your GPU particle systems. And I'm going to go into a bit more detail about some of the things which don't port so naturally from your CPU to your GPU, so things like the collisions and the sorting. And then I'll try and save the last half of the talk to talk about this idea about tiled, so something a bit different to the normal rasterization of particles. So I guess we need to think about sort of the motivation for using the GPU to do our simulation. Because from the year dot, we've always used the CPU to do your updating of your particles, and that's kind of works okay. But I guess it boils down to a case of using the right tool for the right job. And if you've got like 100 or a few thousand particles, then sure, the CPU can do that. But if you're talking about tens of thousands of particles, that starts to be a real burden on the CPU. And as we all know, the CPU is actually becoming quite a sort of a valued resource. So if it makes sense to do this, then we've got the GPU, which is obviously a very highly parallel piece of hardware. So it makes sense to move this kind of workload onto the GPU, especially if the end result is then to be graphically displayed on screen. And the other point is, so we've got direct compute. So this is a dedicated API to doing these sort of general purpose computations. We don't have, the old school sort of GPU particle systems would just render a quad, and you do the pixel shader to do all the work. But actually, we don't need to do this. We can bypass that whole rasterization pipeline. And also, you've got, in a compute shader, you can leverage LDS. So typically, when you compare an algorithm implemented on pixel shader versus compute shader, a lot of the performance win is from using this LDS memory, which you don't have access to in DirectX pixel shaders. So in terms of like the building blocks of your particle system, you can kind of break it down into these steps. You've got the emission first, so you need to emit particles into your system. Then you've got the simulation, so the update for that particular time step. And then you need to do the sorting on the GPU. And then after that, you need to display this on screen. So you can either do sort of your typical sort of camera-facing billboards or something a bit more exotic, so I'll cover that later. So before I talk about the compute shaders, if you look at sort of the data structures required, so fairly obviously you've got like a large particle pool, so you dimension this to the maximum number of particles supported in your system, where each element essentially contains the state for that particle, so your position, velocity, color, and whatever you want to put into that. And it's kind of up to you how you want to implement this as well, if it's sort of a structure per particle or perhaps better still, a structure of arrays for better sort of cache friendliness. And then less obviously, we have another couple of lists here as well. So notably, we've got the dead list. And this is kind of a list that persists over multiple frames. And this is basically an index buffer into your global particle pool. And we're just keeping track of which particles are dead. So it's kind of handy to track that. And also, we've got this sort list as well, which is another index buffer indexing into your particle pool. And we use this for the sorting later on. So first up, we've got the emission stage. So this is a compute shader. And in each thread group, each thread is responsible for emitting one particle. So what I've done, I've got the dead list here. So I don't need to loop through all the particles in my particle system to find a free one. I just use this dead list. And what I've done, I've just put a structured buffer view, a consume structured buffer view over the top. So I can just call consume. And that basically atomically decrements my sort of dead number of particles counter and just gives me the next free index of a particle. So from here, I just initialize the particle. So typically, the spawn parameters come from a constant buffer, so something you would upload every frame. And then you write your new particle state back into the global pool. So next, we've got the main body of the system here. We've got the simulation. So again, this is compute-based, and you can just, from here, each thread is responsible for updating a particle. So if the particle state is alive, then we want to increment its position, velocity, color, and so on. And at the end of that simulation step, it's at this point, if it's still alive, we write it to the sort list. So that actually the number of items in the sort list is zeroed at the beginning of the frame. And then we're just using increment counter just to add each alive particle into the sort list. Conversely, we've got if the particle is determined to be dead at the end of the frame, so if it's dropped through the bottom of our physics world, or if it's kind of faded out to zero or whatnot, we can just add it back to the dead list so we can recycle it for the next frames. And it's at this point here we need to do the collisions. So if you think sort of back to our CPU-based collision, sort of our particle system there, it's kind of easy. You just do raycasts into your CPU-based physics geometry. And so while that doesn't really scale particularly well when you're talking about tens of thousands of particles, that's kind of still quite easy to do. But we need to kind of think about an alternative strategy, something which runs locally in video memory. So perhaps a simplistic approach could be just to have a list of collision primitives, so you try and reduce your world down to a series of planes and spheres and whatnot. The problem with this, excuse me, it's quite a simplistic view of things. An alternative, if you've got a height field-based game, you can quite easily collide against the height field, so that kind of works. If you're looking for some sort of generalized way to do your collision detection, then perhaps consider voxelizing your world, so using a big volume texture. So perhaps each voxel is either sort of solid space or not, or perhaps some sort of hybrid of every technique. So each voxel actually references a list of collision primitives. I've gone for like the path of least resistance actually here, and using the depth buffer for collision. So in this case here, what we're doing, we're actually taking the opaque scene's Z buffer, we're binding it to our simulation compute shader. And so basically the gist is, so we know our particle position at sort of Pn from the beginning, from the previous frame. And we know that it's going to move by some velocity plus in a time step to point Pn plus 1. And the simplest way to do this is basically just project Pn plus 1 just into screen space. So now we've got our particle position in screen space, just x and y. From that, you can then read your the z position in the opaque scene. And all we're doing really, we just need to compare the depth of your particle versus the depth of the opaque scene at that point. So from that, we can tell whether the particle's crossed in past the opaque scene. It's not strictly accurate if you think that actually that's not where the particle has actually collided through the world. It's actually some intersection between down that sort of blue line there. And sure, you can derive that. You can sort of take sort of iterative steps through it to get to that point. But actually just taking the screen space position of Pn plus 1 is normally just good enough. You get away with that. And the other thing to note here is, because you're only using the Z buffer, you don't have any information about how thick, how deep the Z buffer is. So you don't know what's behind that opaque scene. You know, is your particle simulating in free space behind the opaque world, or is it actually inside solid geometry? And actually, there's no way to tell. So we just assume a thickness value here. And if the particle is beyond that at the beginning, then we just assume it's actually in free space and not going to collide. So we've got an approximate intersection point. We just need to figure out a collision response now. So we need a normal to collide against the particle. So, excuse me. So 9 times out of 10, actually, you've got a deferred shaded game, and you can just pull out the normal from your G buffer. That's kind of handy. That's there. For the demo I've put together, actually, I didn't have that. I'm just doing forward rendered. And so all I'm doing is I'm just taking multiple taps, so nearest sort of few neighbors, and from that I can derive the collision normal. The only thing there, you've just got to watch out for depth discontinuities. So if there's a large delta in your Z, perhaps don't consider those samples, take other samples around there. So at this point, we've got our particles collided, simulated, and now they're written into this sort of sort list. And it's now we want to do sorting. So, I mean, you can kind of cop out and not do sorting, and that kind of works for things like sparks, where you can just switch on additive blending, and that kind of works. Well, we want a comprehensive particle system here where we've got sparks and things like smoke. And you can't really apply additive blending to smoke. It just saturates. It doesn't look right. So you've got to do proper standard blending. So this is source alpha plus inverse source alpha. And also, we can't use sort of the things you'd normally use on the CPU. We can't just use like a Q sort or some sort of algorithm sort there. We have to do something which is sympathetic to the GPU, so something that parallelizes really well. And bitonic sort is actually a good choice for this. So this is something we covered in GDC last year, actually. So basically it's using a double for loop to loop through the particle data in different passes. The animation's actually quite instructive on this. There we are. So we've got our sorted data. And then to get this rendered on screen using camera-facing quads, like the path of least resistance here is just to have basically one vertex per particle. So in the vertex shader, so basically we don't need to bind a vertex buffer, index buffer, or input assembly. You just set those all to null in the DirectX API, and you just dispatch just call draw on a number of primitives. And in the vertex shader, all we're doing, we're just using the vertex ID semantic. And that basically gives you an index, which then you look up into your sort list. And from your sort list, then you can pull out the sorted particle data, so typically your position, radius, color, and so on. Then you hand that particle data off into your geometry shader. And it's here is where you do your 4-point expansion. So you're doing your camera-facing billboard. And then after that, you just call a restart strip just so you kick off 2 triangles per particle. But as we know, the geometry shader is not necessarily the fastest part of the pipeline, and if we can avoid it, then that's always good. So we've got, you can just do exactly the same thing, just without the geometry shader, but this time we're just submitting 4 vertices per particle. So if you want to get your particle index, you just take this vertex ID semantic value, just divide it by 4, and if you want your corner indices, you can just do a mod of the vertex ID by 4. So in terms of the submission of your primitives, now we know that the maximum, the worst case number of particles CPU side, but we don't know how many particles we need to submit this particular frame, because that's generated on the GPU. So we have to turn to using a draw indirect API call. So basically, this is like a uint buffer, and each field in that is essentially one of the arguments in your sort of draw direct call. So there's no non-instance version here. You always have to use the instance version. But that's fine. You can just set the number of instances to 1. And then, say, for example, if you so for the geometry shader path here, you need to supply the number of vertices per instance. So with this buffer, you just set 0 that at the beginning of the simulation. And then for each alive particle, so you're adding it to the sort list, but also you want to just do an interlocked add. You just increment that counter by 1 for each particle you encounter. Or similarly, if you've got the vertex shader only path, it's indices per instance. So actually you need to bump that counter by 6. So you've got 6 indices for 2 triangles. So, you know, whether you're simulating on the GPU or the CPU, we've always done camera-facing billboards rendered straight to your render target. And that's kind of cool. That kind of works. But it falls apart when you've got heavy overdraw. So not typically sparks, but certainly smoke. So you've got large billboards, and you've got lots of them sort of laid over the top of each other, and things start to get very expensive. So, you know, and it kind of sucks that it starts to restrict game design. You want your room full of smoke. You don't want to have to throttle back the number of particles. you want to drive through like a cloud of smoke and so on. So we've got ways to mitigate this to some extent. So if you think that if you've got like a screen-aligned particle, typically the four corners have 0 alpha in those areas. So actually it was quite a clever technique to fit your billboard geometry tighter around the alpha edge of your particle. And that's cool. It's not a silver bullet. That's going to might save you sort of 10, 15%. But it certainly helps. Perhaps a more drastic approach is to actually render your smoke particles to an off-screen buffer. So we're saving on fill rate that way. But there's some problems to this. So say if you've got smoke and you've also got sparks, and they're kind of all sort of intermingled. One of the problems here is, so okay, you're definitely going to render your smoke to this off-screen buffer, but what do you do with your sparks? Do you render them before? Do you render them after? Do you render them to the off-screen buffer, in which case you kind of lose fidelity in your sparks? So there's kind of problems with this, and it's kind of really not a solved problem yet. You always have to compromise somewhere. So I'm going to present like an interesting alternative to rasterization. So this is kind of inspired by Ford Plus. So we were here last year talking about sort of Ford Plus and extensions to that. And this is kind of like an interesting tangent to that. So instead of doing tiled culling of lights, we're just now treating each particle as like a sphere, so a point and a radius, and doing tiled culling of particles. So if you think that we've basically got like a scene, we're going to divide it into screen space tiles. I mean, the slides and the code are actually very similar to Ford Plus here, actually. We know that our particles intersect these tiles. And basically, so the first step is we want to find out, we want to build these index lists for each tile, which particles intersect those tiles. So if you look at it sort of from a top-down point of view, we've got the view frustum. Then for each tile, we're basically building up sort of per tile fruster here. And if you think about one tile, that frustum, we've got our global list of particles here. And we want to use compute just to trim that down to just the particles which intersect that tile. So if you look at it from like a sort of thread group point of view, so I've set this up so I've got kind of like 32 by 32 threads in my thread group, which actually corresponds to the number of pixels in that screen space tile. So the first thing I need to do, I need to cull these particles down. So each thread is responsible for culling one particle. So that means in my thread group I can cull 1024 particles in parallel. And then the ones which are visible for this tile, I'm just going to append those to a little list in LDS memory. So the next thing to do, I need to sort. So sadly, I can't sort beforehand. Like in rasterization, I've got the simulation, the global sort of the buffer, and then I do my rasterization. I actually can't do that in this case because if I'm doing my visibility culling, so 1024 particles in parallel, they actually get added to LDS in just arbitrary order. There's no guarantee of the order there. So if the list was sorted beforehand, after this culling stage, the adding of these to the LDS actually puts them in out of order. So I have to sort afterwards. But actually that works out to be a good thing, as it turns out. So firstly, if you're doing bitonic sort, it's kind of proportional to the amount of data you have to sort. And in per tile, we've vastly reduced the number of particles just to the particles which intersect that tile. So actually, our bitonic sort works on a much smaller data set. And the second thing here is we're now doing our sort entirely in LDS. So we don't have to, if we're sorting the global buffer, we have to pull these out of local memory. So we can put as many as we can into local data store, but ultimately, you're moving a lot of memory around. Whereas here, actually, everything's in LDS, so it's really fast. So next up, we've got our list of particles now all sorted. We're going to turn the thread group on its head. So this time, each thread is responsible for shading a pixel. So the first thing we do, we've got like an accumulation color. We set that to black, essentially. And now we're going to start looping through all the particles. So we know each particle intersects the tile, but we don't actually know whether it intersects the pixel or not. So essentially, we do kind of like a radius check against that pixel. So we'd start with the backmost particle. We generate some UVs, we do the texture lookup, and then we do whatever lighting and shading we need to do here. So in rasterization, this is the point where you'd now export that data out, and you'd use the ROP to do the blending against your render target. But actually, we're bypassing all this in compute. So what we're doing here, we're just blending this in a GPR. So we're just blending this against the accumulation color. So we have to do the blending ourselves manually, and that's just source alpha plus inverse source alpha there. So each time we come through a particle, we're just manually blending it to the accumulation color. So once we've gone through our entire list of particles in LDS, we've gone back to front, we've now essentially got our pixel's color and its opacity. So we write that out to a UAV, and that UAV kind of maps to like a texture in screen space. Then once all the tiles have all done their shading, we then sort of composite that back onto the opaque scene. And that's in principle how the tiled rendering works. But we can improve on this. So the first key optimization here is, so believe it or not, you can do correct blending front to back. That works. You've just got to monkey around with the color blending equation. But the key thing here is, so you're starting from the frontmost particle and you're working backwards. And the important thing to note is we can keep track of the opacity of your accumulated pixel. And once it starts to approach opaque, you can then bail out of that loop. So if you think, actually, if the frontmost particle was opaque, you'd be evaluating that one first, and then you could bail out of that loop, and you wouldn't have to evaluate the next 100 or so particles behind it. So it's obviously a key optimization. And the second win here is we can do coarse culling. So we've got so before we do the fine grain culling, we can actually just divide our scene up into like an 8x8 grid, and we're just brute force going through now using a compute shader for each particle in the global list. Which bins does it live in? So essentially using the same frustum testing code, but this time we're writing the particle out into one of 64 bins. So this is something we looked at for Ford Plus, and it didn't seem to make any sense then, because the tiled culling wasn't that expensive, and we only had like 100 or 1,000 lights. But now we're pushing through tens of thousands of particles, and actually coarse culling actually makes a lot of sense. So in terms of the demo, so I'm going to release the source code to this after GDC. It'll be on our Radeon SDK website. So the first view here, we've got some really heavily overdrawn smoke, so we'd expect that to be slow. We've got some smaller sort of sparks, and I wanted to try and get those sort of intersorted with the smoke. Then we've got a bit of opaque geometry. Then we've got a bit of areas where there are no particles. And the other other scene here, this is kind of the worst case. So this is where you'd never let your game designer fly the camera into this point. So we're kind of looking through a load of particles here. We'd expect really heavy overdraw, and we'd expect our frame rate to really take a dive. So we thought we'd have a look at that case as well. So first, for the standard view, you can see, so the compute-based, the tiled rendering is actually, it works out sort of about millisecond and a half faster here. So part of this is leveraging the LDS to do our bitonic sort, and also this early out is really key as well here. So we're seeing a good design win from that. In terms of like the breakdown of costs, so the simulation, well, that's the same for rasterization or tiled. Coarse culling turns out to actually be a negligible cost. Tile culling, that's the fine grain sort of 32 by 32 pixel tiles. That also includes the bitonic sort there. And then the majority of the cost is actually absorbed in the per pixel sort of rendering, the shading of this. There's a few other costs as well, so the emission, there's a few sort of copy structure buffer counts, which kind of take into account the rest. And then our sort of pathologically worst case, so as you expect, so rasterization really, completely blows the budget here, as you'd expect. And tiled rendering, so yes, it's a bit more expensive than the default view, but I would argue that's, for what you're getting there, I'd say that's still quite reasonably in budget. Also, it's interesting to note that even if, for the rasterization, if you're rendering to your off-screen buffer at a reduced resolution, that would still be slower than your tiled rendering. And also, don't forget, tiled rendering is running at native resolution, doing the correct sorting, so it doesn't have any of those downsides of your off-screen buffer. So just to quickly wrap up, because I'm running out of time. So if it makes sense to do so, if you want to push through tens of thousands of particles, we can leverage compute, we can get this stuff onto the GPU, and to work around these things which were kind of easy on the CPU, things like sort of collision detection and sorting. We've got bitonic sort, and we've got depth buffer collisions. And also we looked at tiled rendering. So in the cases I looked at, you can try this in the demo yourselves when we release it. It works out faster than rasterization. And it's particularly good for these heavy overdraw cases. So hopefully opens up some more design possibilities here where we've got much thicker smoke in those areas. And also in terms of future work, I mean, as soon as I get back to the UK, I'll be hacking again at this and trying to add some more things in. So things like sort of now each pixel, we're not overdrawing it loads. Perhaps we can sort of dedicate some more time to actually making that pixel sort of really count, shade it better somehow. And don't forget, now we've got our pixels in, our particles in LDS. So actually, we can sort of iterate through all those. Perhaps we can do some interesting volume tracing through those. And also quite like the idea of adding your semi-transparent geometry into this as well. So you're not just compositing your particles back onto the opaque scene, but perhaps also the correctly sorted alpha blended geometry as well. So lots of possibilities here, and sort of quite exciting opportunities, I think. So I've kind of run out of time. Do we have time for questions? No. I'll be here anyway, taking questions, or email me, but I'll be around for the next sort of 10 minutes or so. Cheers.